Okay, hello. Can everyone hear me? Awesome. Thank you all so much for this honor to be here at such a historic institution to share some of the things that's been really the science of my 42-year-old life. And again, if you see anything that's very interesting to you, please feel free to send me an email. Yes, Jess is laughing because she sees it, that London is red, just like the background. All right, so what exactly is quantum? Well, my title I kind of fitted to you a bit. I said the quantum is here. Well, actually, we are celebrating the 100th year of quantum science in the world from UN's International Year of Quantum and Science and Technology, because quantum has been here for at least 100 years. What do I mean by that? Well, as you see here, physics is like any other subject. In mathematics, you have calculus, you have algebra, you have arithmetic. These are different subject matters. In history, you have African American history, you have European history. In physics, we also have the same thing. And typically, when you take your first physics class, you study something that looks like the study of motion. So if you were to ask Siri what physics is, it's actually the study of any of the natural sciences of quote unquote matter, involving the study in its fundamental constituents, motion, behavior of that matter, how it moves through time and space, and you really relate all of this through two typical things, energy and force. And how you did this in the first part of physics, the study of classical motion, is that you started off with defining things like displacement. So how can I move from point A to point B? What happens if I leave things at rest? They'll stay at rest. And then it continues all the way down to describing things like work, energy, power, the work energy principle, things like equilibrium. All of these is what we learned in Physics 1. And then if you take a step back, then you can also, in Physics 2, you can apply these same classical laws of motion to not large objects like the world or celestial bodies or cars or people, but you can now look at what happens when you have electrons moving along a wire, or what happens when you have these electrons in the influence of a large magnetic field. And that field of study is called electricity and magnetism. Electricity and magnetism. And the form of these equations, right, the same one that describes how your car will be moved or tugged in a specific way, that same force, that same energy can now be described from things that are very, very, very large to the things that are very, very, very small. In this case, these are electrons and wires. Now, unfortunately, about 100 years ago, we found out that all of these great laws could not describe everything accurately. And what you see in the top left is that we had a quote unquote failure of classical physics. So everything that we thought that we could do once things got to be really, really small, such as atoms or subatomic particles, or if we even looked at something like light, what we noticed was light a continuous stream of a wave, or was it many, many small quanta of light or photons that move in that stream? So this started a large debate of something that's called wave-particle duality. And then you also had things like the uncertainty principle that you might have heard of. But you also have many implications of what does an atom even look like? Is it an electron cloud? How can we see these things? And that whole field of body is what we call quantum physics. Now, today I would be remiss if I didn't point out that in this same building there was a person by the name of Thomas Young. He shared my name, Thomas, and he was the chair of the natural philosophy at the Royal Institution. And there, what you see to the left is a colorized figure from a lecture that he actually presented in 1802. So many, many years ago, he stood in this same spot and he presented to what I will present to you today. And in that vein, we'll hope to do an experiment that will show this same idea of diffraction. So this is the interference, constructive or destructive interference of waves. Does anybody own a pair of Beats headphones? That's how exactly, when you hit the noise canceling, that's exactly what happens. It matches the actual wave frequency and amplitude. And with that matching, then it cancels it out such that in this case with light, what you would see would be a dark fringe, but all the bright fringes would be something of amplification. So at that same phase, at that same frequency, you would then see those bright fringes there. So what you see here is that we have two different types of hair. And with respect to that hair, we have two laser pointers, and the laser pointers then interact with that particular smaller bit of hair to then create what's called a diffraction pattern, where the bright fringes correspond to where you have this amplification or constructive interference, and the dark fringes are what you would see, what we call destructive interference. And you can then apply the laws of physics to actually tell, as you'll see, that the spacing between the fringes are different. Does anyone know why? The hair is different. So with a different diameter, then you can actually measure how large the hair is on there. And this this idea of diffraction actually was way back in 1802 in what would still be considered to be classical physics. Now, at the time, there was also around 100 years later, and this just shows you in a double slit, if light acted as a wave, and then what you see is that it spreads out, and now you have these fringes that occur. And this is the wave optical interpretation of the double slit experiment. However, during this time from 1802 to around 1905, the time of Einstein and others, there was a lot of evidence that waves don't necessarily act as, light does not necessarily act as waves. And actually this idea that light acts as a particle was much, much older than even 1802. That came from Newton 200 years previous to that. However, Einstein came around and others with him, and in this paper, his famous paper on the photoelectric effect, he really wanted to study what would happen if you had a stream of photons or small quanta of light, and you interacted that with atoms that were on a piece of metal. And at a high enough energy, what he found was that you would knock the atoms off of the sheet of metal, and we call that the photoelectric effect. And if that was the case, where you would have a double slit experiment, then you would still have these fringes, but you would have the stream of photons that some would be bounced back off of the screen or the original slit, and then some would not bounce on that. Now, that's not the complete story, and this is how quantum is extremely fun, right? Because de Broglie came around, and what he described for the nature of electrons specifically was that not only do electrons or quantum objects like photons exhibit wave-like properties, but they also exhibit particle-like properties. So you're not one or the other, you're both at the same time, which is an extremely quantum type idea, right? So how exactly would that look? Well, on the left, what you see is a recent paper in the New Journal of Physics that shows an experiment for a double slit experiment with an electron gun. And what you see is that each particle at a time adds up to be what looks like these fringes at the end. And if you look on the right, what this looks like is now you have, oh no, is it the right one? Wrong figure. Okay. Well, what you would see is so on the right-hand side, what you actually would see when the electrons act as waves and particles at the same time is that you have that same wave phenomenon. However, there's an option that it goes through one or the other or through both at the same time. And that was what is actually happening to the left. Okay, awesome. So what you see here is the wonderful world of the map of quantum physics. And everything that I described to you previously is all the way in that corner. So this concept of atomic spectra, which you'll see a little bit later, black body radiation, the photoelectric effect, these are all pre-quantum ideas at the interface of the discussion, public debate of is quantum real, what is happening, all of these things are there. Now, for those that are lucky enough to have a full-fledged quantum mechanics course, then you'll start to recognize that you see other things like the wave function or the quantum harmonic oscillator. And if you move down and down and down, what you'll also realize, back to my original discussion, that quantum has already been here. It's actually ubiquitous in our life today. I wouldn't be able to give this presentation with you without having some type of quantum. All the quantum technologies, what we as scientists call quantum 1.0, are down in the bottom left corner. There you have solid state theory, the band theory of solids. How I demonstrated the diffraction was all done with laser pointer. We use laser pointers all the time. We use QR codes to scan our groceries. The CCD, or the charge coupled device, or even the transistor, which has been around since 1950. These are all quantum devices that we don't even think about today. Now, what I mean by quantum is here, and quantum will hopefully revolutionize what we're talking about. I'm actually talking about quantum information science, which I'll explain a little bit later. But as I stated, quantum was there 100 years ago. And I always love showing this photo because there is the very recognizable Einstein, right? And he's actually at what's called a historically black college and university by the name of Lincoln University. So at the same, and then on the left, what you see is a news article about the Einstein-Podolsky-Rosen paradox in the New York Times. At this time where the picture on the left was taken, Einstein was as famous as Beyonce. He would come into town and everybody would put on cowboy hats. No, just kidding. But he was one of the most sought after speakers all over the world. He lived in the black community of Princeton University in New Jersey, and he elected to go to Lincoln University to talk to physics students at that time. And at that time, he also, it says on there, and I always love showing this to my students, it says scientists and two other random colleagues, which is Podolsky and Rosen, they found that within their paradox that this was not complete. So this is New York Times at the height of the career 100 years ago. And believe me today, that quantum is just as interesting, if not more interesting, in today's world. So, if quantum has been here for 100 years, then what exactly do I mean, right? So before I showed you this map to the left, and I related it to the demonstration that we did earlier, all of these ideas of photoelectric effect, all the way down to the 1950s of what a laser is and why we have quantum technologies like MRI machines and other things like that. And what I meant by quantum in our case, that now quantum is here, is that quantum information is here. And specifically, quantum information is more than just physics. I say that as a physicist, right? And it's more about controlling quantum objects to improve technology. So things you may hear about the next quantum internet is that it's an unhackable internet. Or you may say that you may see things that like quantum computers can revolutionize the way that we live and or solve climate change, right? So this is this idea of using quantum physics and another physical principle like information and putting these two objects together to solve problems. And typically what happens there is that we use what is called qubits for information. So these are small size atoms or subatomic particles. They have to be really, really cold. So that's why you see, once you see a quantum computer, you'll see actually the cryogenics that control and also cool down the system such that it can reach temperatures on the order of 10 to almost millikelvin, depending on the system. Or you need things to be both small and cold. So that's what we mean by quantum information science in a nutshell. And if you zoom into this idea on this, so all the way into the middle is what you see quantum information, then you can see this block sphere. So this is the physical representation of a qubit. So it's not only in the one state or the zero state, but it can be in all states all at once. You can also see that this idea of a quantum computer, that's the silver part is your representation of our current quantum computing system. And then what you see to the left is what's called quantum simulation. And we'll get back to that idea in 1 second. The other things that you'll see is this idea of quantum teleportation. So this is sharing information across long distances, not moving people, but moving quantum objects. And then you have the quantum internet and quantum complexity. There's also interesting things that go on with quantum sensing, like quantum biology and trying to make better medicines and that type of thing. Now, in this video, we see Prime Minister, our former Prime Minister of Canada, Trudeau, whose physics teacher should be extremely happy with what they have presented to them. However, we won't make you watch a YouTube ad to listen to it. But I encourage you all to listen to it a little bit later. But the bottom part is a quote from Richard Feynman that says that nature isn't classical, explicitive, and very Feynman-like, to cuss in a quote in a paper. But then if you want to make a simulation of nature like one of these quantum simulations, then you'd better make it quantum mechanical. Because previously, using computers, and this is in his famous paper from 1981, but 1982, where it talks about how one could really simulate physics with computers in the way that physics was supposed to be simulated. This was the first presentation of what a quantum computer could be. So that gives you an idea of what I mean by quantum is here. Even though 100 years ago, right, in 1800s and all early 1900s, there was this concept of quantum mechanics. It took all the way to around the time that I was born in 1983 that now we have this idea of actually using quantum mechanics to study the physics that's around us. And just since that time from 1982 to the release of the first real textbook on this from Mike and Ike, which was in 2010 or so, in that 2010, which a book that was based on NMR computing, there was a little tiny line in it that said that there was a group from Yale that was working with IBM. And in that particular line, now what you have is that right now, today, on your computers, you can go to ibmcomputing.com and log into a quantum computer and do demonstrations on the internet. And the field is moving that particularly fast, and the investment is vast and large. So just to give you an idea of what that looks like, here's what we have. It's what's called the current quantum computing market map. On the left, you have a lot of end users of the expectation of how quantum computing can change our lives. And that should be companies and names that we recognize, right? And then what you also see is that not only do you have applications, but you also have people that just build their entire companies along software. And there you still have some of the big names that you notice. However, you have all of these little tiny names. Some of them are from the UK, right? If I see some, I can point some of them out. And then on the right-hand side is what you have the quantum computing processor units, or QPUs. And there's you see the different modalities or the different types of qubits that people are working on developing. So you have IBM and Amazon and D-Wave and others that are working on superconducting type qubits. So this is this concept that you can build a circuit and then you can cool that circuit very, very low to have this superconducting phenomenon and then use that to do quantum computation. You also have ion traps. So these are taking specific ions of atoms and trapping them in such a way that you can then control the quantum states to then do computation. And some of these are even publicly traded companies like IonQ. The others that we have is neutral atoms. So this is cold quanta is no longer there. It's actually called inflection, and it's out of the UK. We also have silicon-based companies. PsiQuantum is out of Bristol. It's a photonics-based company, which we'll talk about a little bit later. And then you have very small companies like AeroQ, which is electron and helium on helium-type qubits. And amongst this entire industry that you see to the left, you also have supporting technologies. So these are photonics-based companies, our electronics-based companies, our cryogenic-based companies that support these quantum companies to help them build the first utility-scale quantum computer. So this is really what I mean by quantum is here. There's an entire industry that's all over the world. And what do I mean by all over the world? So right now, it's a $42 billion industry and investment all over the world. And what you'll see, places like the UK, we have something like $4.3 billion invested. In places like the United States of America, at the time, we have around $5 billion invested. In places like China, we have something on the order of $15 billion, even though that number is debatable. Some think that it might even be 10 times that amount. And a very, very interesting thing that you will see a little bit later is that I am from the great state of Illinois. And in Illinois, this is Chicago in Illinois, that we have 2 out of every 5 US dollars in quantum in the state of Illinois. So if we go back, what that means is that in the city of Chicago, in the state of Illinois, we actually have more investment, more activity in quantum than a lot of nations that are way larger in size than us. And I'll show a little bit of our plans that are being built there. Just like the map of quantum physics, I just wanted to give you an idea that there is a similar map for quantum computing. So in that, it talks about these basics it talks about going from quote unquote classical computing, where you're based on a bit of ones and zeros, all the way to qubits. And then you can start to talk about, really and truthfully, one of the largest areas of activity and importance and why we may not see quantum advantage right now is the fact that there's not a lot of good quantum algorithms that can prove quantum advantage. As a result, which you'll see a little bit later, in the state of Illinois, we have a National Quantum Algorithm Center that's being built. And there to the left, you have these physical realizations, so you can get an idea of all the different approaches that people are hoping to have this large-scale quantum computer. All right. So this gives you a closer idea of what I mean that quantum is already in Chicago. So my university is the home, that's right there. And then we have national labs. So Fermi National Lab leads one of our National Quantum Information Science Centers. Argonne National Lab leads the number 2 of 5 of the National Quantum Information Science Center. You have universities that are all involved, and then you have some of these startups that are popping up all over the city. The other big investment, so PsiQuantum is an anchor tenant in a $20 billion facility on Lake Michigan that used to be the site of the U.S. Steel Works site, where a lot of the steel that industry of the United States of America back in the 1900s was at that particular site. That's now been refurbished for the purpose of quantum with hopes of building an economy all on the south side of Chicago. On that, we also have tenants like DARPA. So this is the Defense Agency of Research. DARPA makes early investments in everything from, we call it a Roomba. So this is like the vacuum that's autonomous that works around. Other things that DARPA has worked on has been GPS, the internet, all of these things. And that's also there. And then, as I stated earlier, IBM has the National Quantum Algorithm Center. And the idea is that you have hardware, you have software, you have workforce development. It's all on the south side of Chicago such that it can encourage communities to see it, to believe it, and then achieve what we would hope to be a utility scale quantum computer in Chicago. Now, this might ask, or a question that I get asked all the time is, how did I get involved in quantum? And in particular, I got involved in quantum because every Black physicist has an origin story. And what you see to the left, does anybody know who it is to the left? Black Panther. He got it. I would imagine that Black Panther would be a part of the Blackett fam, right? Blackett Lab fam, because he got his PhD as a student athlete from Oxford in physics. And then to your right, you see Killmonger, or Eric Killmonger, who got his PhD in electrical engineering from MIT. So as a physicist that works in engineering, I like to say that physics is good and engineering is bad. No, just kidding. But this just gives you this idea of every Black physicist has an origin story. Now, mine actually comes from the fact that Black physicists have worked in quantum since there was this idea of a Black physicist. So the first Black person to earn a PhD in the US in anything was this gentleman by the name of Edward Boucher. And he was the sixth person to earn a PhD in physics, period, no matter race, color, creed, whatever. He worked in geometric optics because studying minerals were something that was good or of interest at the time. However, he had limited opportunities when he graduated from Yale in the 1800s. However, he dedicated his life to educating others, especially at the K through 12 level. And now, currently in the US, many institutions and programs are named in his honor. The second Black physicist that really encouraged my journey is one by the name of Elmer Imes out of Fisk University. There's this fantastic article in the Symmetry magazine called #Black in Quantum that tells more than what I'll be able to tell about his story today. However, he was the second Black person to earn a PhD in physics, this time from the University of Michigan in 1918. He was first faculty of all places in my hometown of Albany, Georgia. But then he moved on to Fisk University, where he built an atomic spectroscopy lab. And he actually published the first journal paper from an African American in the Astrophysical Journal and in Physical Review in 1920. He was an active member of the Harlem Renaissance and a civil rights activist, and he advised Carolyn Parker, which you'll see a bit later, who was the first Black woman to get her graduate degree in physics at MIT. Now, this is actually data from that first paper in the Astrophysical Journal, where he was studying the atomic spectra of things like hydrogen chloride or diatomic molecules. And so what I mean by atomic spectra, you'll see a little bit later through what is called the flame test. So if I could get help turning on the flame. It's a tradition at the Royal Institution to do experiments live. And when I told my students I would do this, they got very afraid. But don't be afraid. So in order for us to show kind of what he was studying, which would be the atomic emission spectra, we have a series of different metals in spray bottles. And we're performing what's called a flame test. Here we have our flame from the torch here. And how this works is that each one of these bottles has a liquefied different metal in it. And when I spray the metal into the flame, then it will heat the metal into an excited state, and then it will then relax into its relaxed state. But by heating it up, I add energy. And by adding energy, then it needs to emit this energy. And what actually happens is that you have a different color. So here with copper, you see this bright flame here? And strontium gives you another flame, our emitted spectra. And something like sodium will give you an even different color. So depending on the color that was emitted, don't want to burn anybody up. Depending on the color which was emitted, one can tell what particular metal it is, right? So you can use the color or the spectra to then identify what that was. And that's exactly what Professor Imes is doing here. However, he's not using colors. He's actually in the infrared, and he's measuring this with a now we would measure it with a camera, but there he would measure it with a particular photo detector and then take down each data point and then send it off to have these graphs of different spectra. But depending on the fingerprint of that infrared spectra, then you would know that it would be hydrogen chloride or hydrogen fluoride or one of these things. And again, this was done in 1919. Let's see here. All right, awesome. Okay. So the next Black physicist that again talks about my story is really instrumental to a lot of what I'm doing currently is Herman Branson. So if you remember that Einstein article where it was Einstein and these two other randos, well, one of the other randos was Podolsky, and he was currently at the University of Cincinnati. And Herman Branson, he studied there and particularly studied what's called X-ray crystallography. So this is this idea of Linus Pauling, who he actually worked with during summers at Caltech, to look at things like the double helix and actually measure that particular structure. He did all of this at Howard University, which is in Washington, D.C. And the other thing that he also did was here in the American Journal of Physics, he published this article which said the physics training for the Negro student. I was actually a professor at Howard as an assistant professor. So when he wrote this, he was an assistant professor at Howard. When I read it, I was an assistant professor at Howard. And it really resonated with me for many, many reasons. So there at the time, the biggest thing that was on the mind of everyone in 1942 was the Manhattan Project. And in particular, World War II. And the argument that Professor Branson made there, which I do not have in, is that these are the things that we should encourage our students to study. These are the places that they should go to, and this is the type of mentoring that HBCUs or historically Black colleges should do to prepare their students for training in physics to contribute to the war effort. How many people have seen Oppenheimer? Fantastic movie. How many Black people did you see in Oppenheimer? There was one. That one person was J. Ernest Wilkins Jr. He was, quote unquote, dubbed the Negro genius because at age 13, he went to University of Chicago to study. And at age 19, he received his PhD from the University of Chicago. He worked with Wigner's team, like the Wigner crystal and others at the metallurgical lab in Chicago. And he's still to this day, there's the Wigner-Wilkins spectra that people use in nuclear physics. And he had a storied career and encouraged many African-American students to study physics. And interestingly enough, in this very small font that you'll see, is that if you remember from the movie, that they had many different sites all over the US, and they wouldn't tell people where these sites were. And one site in particular was called Site X. Site X was at Oak Ridge National Laboratory in Oak Ridge, Tennessee. And once they found out that this was a Black person, they said, oh man, you can't bring him down to Oak Ridge. He has to stay in Chicago. Well, Edward Teller wrote this letter to the director in Columbia University, and he said, hey, we're looking for our best and brightest. Or we found out that he was not allowed to go for segregation. However, we think that it's going to be a very, very good idea to send the entire team down. And all of those results ended up where we are today. But this is just a storied vision of kind of what it was like to be a scientist at that time. Now, another person that I mentioned previously was also in the Manhattan Project, and that was by the name of Carolyn Parker. So she was the mentee of Professor Imes at Fisk University, and she graduated with her physics degree from Fisk, and then went on to go to MIT during this time, where she would have been the first Black woman to get her PhD in physics. However, due to complications from the environment of working with the nuclear materials, then she passed away during her graduate studies during that time. And it wasn't until Willie Hobbs Moore in 1972 where we would have the first Black woman in the US to get a PhD. Another great person that came from all of this was Warren Henry. He was at the Naval Research Lab during this time. He was an experimental condensed matter physicist like myself. So there he's on top of a magnet, cooling it down to study materials. He was a very storied scientist, so he was a fellow of APS and ASSS. A fantastic scientist there, worked in many different positions. He started the program actually at Morehouse College. And interestingly enough, his data still to this day, so a lot of people have kind of moved away from using Holiday, Resnick, and Walker. But when I taught at Howard, I would always tell the students that in chapter 42, in this figure, this was data that was taken at their university, which was actually really, really cool. Another thing that I found in this is that at Argonne National Laboratory, which is around 30 minutes south of Chicago, there was, at the time, what's called the Atom Scientists, 10 Negro scientists at Argonne National Lab helping the race to harness atomic materials. And even though I'm only able to show 4 scientists here, there's actually 10. And they did small highlights in Ebony's magazine in the 1949 issue that showed all of the great work that these scientists did. And really and truthfully, since that time, inside of the Department of Energy ecosystem, now 17 national labs, I doubt you would find 10 or more Black scientists in that space. Now, what exactly is an HBCU? I just talked about it a lot and didn't necessarily explain it. So in 1964, there was the Higher Education Act, that stated that any Black college that was formed or established prior to 1964 with the principal mission of educating Black Americans would have this particular designation. And that designation still holds today. And because of really the fruits of what slavery and where the fact that still in 2025, most African Americans live in the southern United States, is that 101 of these institutions exist now, and they are all throughout the southern United States of America. What you have to the right is an article in Science magazine that was called The Missing Physicists. So where are the Black physicists and where do they come from? And the dark colored circles, so over this 10-year period, the dark colored circle shows that only 2 physics departments had more than 100 graduates in physics. And then as you see, from 50 to 59, it was only 11 departments and 13 departments and 21 departments. I happened to be at Morehouse College at that time, and we'll talk a little bit more about that later. But this graphic really and truthfully shows the power of historically Black colleges and universities in the US. To the left, you have your number of Black Americans that received doctorate degrees from 2015 to 2019. And then on the right, what you see on this the bottom axis is the enrollment, so how large these institutions are. And what you see is that you see these outliers. So Spelman College is an all-women's institution in Atlanta, Georgia. And what you see is that they produce more African-American, and then now in this place, women, than places that have way, way more student bodies than they do. And even the small place that I went, Morehouse College, still has this same idea of competing with these large universities like University of Florida. So for me, I was just a kid from Albany, Georgia, right? I read a book about Black astronauts, and in that book, there was an astronaut by the name of Ronald E. McNair. For those that don't know who Ronald E. McNair was, he was a laser physicist who passed away in the Challenger accident in 1986. And then I had what was called a Panther mom. And my mom in Albany, where I was from, we were actually ahead of the curve in taking physics out of the curriculum. Right now, only 40% of US students take physics. And that number is even lower when it comes to any type of women, Blacks, Hispanic, like taking physics just from jump is not what's happening. But my mom fought with the school board such that I was the only student in my district to take physics at the time. I attended Morehouse on a Ronald E. McNair scholarship. I interned at NASA and NOAA, and then I worked as an undergrad in what was called the National Nanotechnology Initiative. And that is the precursor to what we have now in the US, which is the National Quantum Initiative. And there you see, that's me and my dad. I was very small at that time. My mom is there. So this is when actually the day after I got married in Chicago. And my PhD advisor, the great Jun Kono, there at the lab. And then zero gravity flight, when I worked at Morehouse, I was able to take students on a zero gravity flight to do an experiment. And then I would be remiss if I didn't point out my two older sisters, which I am taller than both of them now. So that formula is actually right place, right time, right? I happened to go to Morehouse College where it was not a strange place to be a physicist. I also happened to go to Rice University. Right now, what you'll see hopefully a little bit later is that I lead a team of a majority of Black women in science and engineering. And when reading a book on how do you create Black scientists and engineers, there was no literature on Black women in physics and engineering. That actually first PhD came out in 2024. Fantasy Nicole is her name. And so what that did was that led me to research the Black males in engineering, which was me. And what it said was that there you see Willie Rockford, another past president of NSBP. He was my undergraduate mentor at Morehouse. This is the day I defended. And then my PhD advisor is there, Jun Kono. And it really states that 4 factors help Black Americans, or Black males rather, get their PhDs in physics and engineering. It's regardless of their socioeconomic status or the fact that they're in a single or a 2-parent home, it's the encouragement of their mother. My mother, still to this day, she wanted to log in and FaceTime to watch this talk. So she's very involved. Your undergraduate advisor matters a lot. So having that relationship with your undergraduate advisor. The third thing that they said was your current PhD advisor's ability to integrate you into the environment that you're in. And Jun Kono did a fantastic job at that at Rice University. And last but not least, they say that you get closer to God, whatever that means. And it's really, truthfully, it happened to me. But it also, I think, is more of finding a community outside of your academic community to be a part of. And that's how you kind of create that situation. So the other person, again, like I said, I was lucky enough, right place, right time, is that you have our first physics major, which was Walter E. Massey. So he got his physics degree from Morehouse in 1958. He was a theoretical condensed matter physicist when he graduated from St. Louis University. Washington, St. Louis. And he's had a storied career in everything that you could imagine. He was even the chairman of the Bank of America during 2008. He was the president of the Art Institute of Chicago. He was also the National Science Foundation director for some time, and he was also the chancellor of the California system. So anything that you could ever imagine doing in physics, Dr. Massey was doing that. And I was lucky enough there when I graduated in 2005 to see what a Black physicist would look like very up and close. This is it's not a mystery why the Morehouse numbers are the highest that they always are, because it's not odd to feel like you can be a physicist. Fast forward, now I live in Chicago. He lives in Chicago. I see Dr. Massey all the time. It's fantastic. The other thing that I wanted to point out is that he studied quantum fluids in the 60s at Argonne, and actually was one of the co-founders of the National Society of Black Physicists. At the first National Society of Black Physics meeting, which was a series of talks, he gave a talk on quantum fluids, which I think was really, really cool. So back to Herman Branson. This part is on. Oh, it's okay. At Howard, when I was there, I actually got to meet Gary Harris. So those that work in quantum know how important silicon carbide is. At Howard University, we grow silicon carbide through the nanoscience facility that Gary started. He was also the PI of one of the large NSF STC centers. So what did that look like for me at Howard? So in 2015, I started there. I had 2 donated optical tables. I was able to then work within that system of the program that Gary started. We added some students and some lasers. We were able to get our first paper on quantum metamaterials. Now I think it's up to 300 citations or so from 2018. My first graduate student graduated with his PhD, which was one of my little Morehouse brothers, Chan Kiao. He graduated from this paper in Optica where we created the first terahertz flexible photonic crystal. And then to the left, Fiona, which you see here, she started growing these great materials in topological insulators and whatnot, their large crystals for terahertz. Unfortunately, then the pandemic happened, right? And once the pandemic happened, I went to IBM and we were able to come up with this program, which was called the IBM HBCU Quantum Center. There we have 27 institutions, regionally sparsed out between the type of institutions, so PhD institutions all the way to all undergraduate institutions, studying different types of quantum information. And now we all work together and we're in our 5th year. We have cohorts of around 30 students a year. We have over 100 faculty that are involved. It's been a fantastic program, and it's part of the reason why I was invited to London this time around is that they had a partner meeting there. For anyone that's interested, we also have the Women in Quantum series. So there at Spelman College, we take Black women quantum scientists and we fly them to Spelman to give talks on what they're doing and their life story. Kayla Lee was our first speaker. And then we also had one of our graduates, Victoria Adebayo, who was one of my undergraduate students at Howard, and now she is studying at Harvard, the other HU. Okay, so a little bit more about kind of what we're working on in quantum. So there's my fantastic research group. We call Evan our underrepresented minority, but Evan doesn't mind. But we work in quantum computing, which are AI applications, so neural network applications of quantum hardware. We also work in quantum networking, which I'll show a little bit later, light matter interactions, integrated photonics. There to the left, you see our first journal cover, which was a quantum game that I developed on Mancala. So each one of the blue lines is each blue graph is a different type of quantum strategy. One involves the quantum Zeno effect, one does not. And it's all based on this idea of Mancala. Has anybody played Mancala before? Awesome. So you have 2 stones in a pit, and there's very strict rules that go on the game as far as which way you can move and the order of moves. So if you just have 2 pits and 3 stones on the first 2, so the first move and the second move, that follows classical Mancala. And what you'll see is that your probability of these Fock states, because I'm treating them as bosons in Fermi-Hubbard model, is that you will be able to go from pit to pit, and that follows the classical rules of Mancala. However, in the third move, which is theoretically in classical Mancala, this is how you would win the game. What actually happens is that you have a probability of winning the game. And not only do you have a probability of winning a game, then you start to see more quantum effects happen such that you violate the rules of classical Mancala, where you no longer have to go in this counterclockwise area, you can actually hop back. So you have interesting things that happen just with 3 pits. We expanded this into many, many pits and many arbitrarily large states. So now in a quantum network, we have, using the abilities that are strategies from the Mancala game, you can then apply that to a quantum network and have an arbitrary set of states in this way. And then last but not least, so you can see that this is the real quantum network that's happening in Chicago. I'm also involved in a continental scale type idea. So this is sending photons with satellites from places like Oak Ridge or Purdue all over the US. And then also locally, we work with inflection. to work in with respect to having a local quantum network on our campus. Now, quickly, and then I'll love to take questions because I'm sure some of the questions have to do with this right here. Is quantum really here, right? And in particular, you had our friend Jensen, who gave this speech earlier this year that said that quantum was going to be 25 to 30 years away, right? All these investors got upset. I actually got encouraged. When I started studying quantum, people said this would never happen. Now we have people thinking that this is going to happen in some time. And what was even more interesting is that 25 years ago, NVIDIA actually produced their first chip ever. So if he thinks that we're on the same time scale of an NVIDIA chip, then I am very, very encouraged by this. And then in this National Academies report, essentially what they're arguing is the argument that I make is that we have to move beyond laboratory small qubit systems into very, very large scale systems. So thousands or millions of qubits is the idea there. And essentially the way that what we can do now, so that's the check marks, is that we can start a qubit, we can run a program, we can stop a qubit, we can measure them, we can do everything that you want to do with a qubit at a very small scale limit. The problem happens when you go to millions and thousands of qubits. There we cannot necessarily connect them with other qubits. That takes a large quantum networking thing. And then the other aspect of it is that we cannot keep them quantum the whole time. This is the idea of maintaining coherence or maintaining entanglement for large amounts of time. What I mean by large amounts of time, like milliseconds, is a large amount of time. That is something that we cannot do right now. There are also problems that we can't solve. We can't predict the weather. We can't necessarily do logistics in some way. We maybe can do quantum chemistry. We don't necessarily know yet because we don't have the systems that are able to do it. However, we can do things like factor large numbers, right? So that's why a lot of people, you may have heard something like post-quantum cryptography. Why that matters is that once the quantum computer comes along, people can take your old data and then process it and then break encryption. So that's the issue, right? So even though it's not a problem of today, it is a problem of today. The Google and their Willow chip, they had a fantastic result recently where they showed a very difficult problem on quantum computing and made the stocks go crazy and wild. However, what you see in this graphic here is that you have, quote unquote, commercial usefulness and you have difficulty. So this means harder than a supercomputer, one that would be bigger than this entire building to do. So they were able to do a very, very hard problem that is not relevant to a lot, right? And in order for us to go into this larger portion where everybody wants to be, that's where we need millions of qubits. That's where we need to compute them together. That's why we need them to be stable. So that's what people mean by it's far off. However, rapid changes happen every single day in this aspect. And in particular, DARPA, if you go to DARPA's website, they have a list of problems which are being vetted where they actually think that these problems will be able to be solved. Now, I would like to close for questions, but really and truthfully, I like to show two different figures. So here we have, in my hometown of Albany, Georgia, it's where the Albany movement happened, which was considered to be in the civil rights movement, the first place where Dr. King, quote unquote, failed. But actually what happened was he learned everything in quote unquote failure in Albany, and he applied that to Birmingham and the bus movement and Rosa Parks and everything there. And what I encourage young people to do, and in this context of quantum, is that we need leaders not in love with money, but in love with justice, not in love with publicity, but in love with humanity. And more than truthfully today, as I return to the US, I think about this every day. So with that, I'd like to take questions. Thank you so much to the audience. Thank you so much to the Royal Institution and their demo team. Professor Jess Wade, She's an amazing person. I give her book on nanotechnology to every small child that I know in the US. She was nice enough to bring me a Black Arsenal book all the way to California. She's amazing. To Professor Mark Richards, AKA DJ Chemist, who's a legend overseas, the Blackett Lab Family, all of my collaborators in the US that helped me develop this, and then Stanley and Marvel, of course, for inspiring all the Black physicists in the country. So with that, I will be more than happy to take questions. Thank you.